Do you love books? Do you wish you could hear some insights straight from the author themselves? Join Sam Hankin, your host, as he interviews top-selling book authors and dives into interesting and unforgettable discussions here at The Avid Reader.
Hi, everyone. Welcome to another edition of The Avid Reader, brought to you by Wellington Square Bookshop. Our guest today is Jason Steffen, author of Hidden in the Heavens, How the Kepler mission's quest for new planets changed how we view our own. Jason is an astrophysicist. He's the assistant professor of physics and astronomy at UNLV. And he was a member of the Kepler Space Telescope mission, which is what this book is about. The Kepler mission, designed to find exoplanets, of which Jason is the discoverer of a few, named after Johannes Kepler, who was a polymath whose work in math, astrology, philosophy, music, allowed scientists in later times to stand upon his shoulder as they discovered more about our universe and its mechanism. Jason serendipitously ended up figuratively riding along with Kepler as it succeeded in its mission, along with some travails, and added so much to our understanding of the universe, stars and planets, which underscores the subtitle of the book because it also lent itself to a greater understanding of our own starship Earth. So welcome, Jason, and thanks for joining us today.
Thank you for having me.
So I guess let's go back to Kepler, the man. How did the name actually attach itself to the mission?
So that's a good question, because I didn't really know until I was partway through writing the book what was going on. So he originally devised his laws of planetary motion that moved us from, it moved us definitively away from the heliocentric model or the geocentric model with the Earth at the center and put the sun at the center. And then he showed that it wasn't on circles, that you had to have ellipses or hyperbolas to describe the orbits of the planets. And so he devised his three laws of motion, but then the important thing for our purposes is that he predicted that Venus would transit the sun. And it was a few years later when the transits of Venus were observed. And so it was really Kepler's predictions of the transits of both Venus and Mercury that kind of made it appropriate to have his name attached to this mission, because this mission looks for the same transits of other stars, or of other planets orbiting other stars.
One of the things that always, when I was reading science fiction as a kid, one of the things that always got to me was, and you mentioned it in passing, is the idea of Vulcan or Nemesis. Talk a little bit about why that was thought when in actuality it was something completely different.
So that was, if I can remember the name, I think it was Jean-Joseph Le Verrier that made the prediction. So he first made the prediction about the existence of Neptune. Basically, the planet Uranus had been observed for a while, and astronomers found that it was deviating from its nominal course. The orbit wasn't tracing out exactly what you would have predicted from the combination of Kepler and Newton's work. And so Le Verrier predicted that there might be another planet outside of the orbit of Uranus that was perturbing its orbit and causing its orbit to change. So he sent his prediction to a few astronomers at the Berlin Observatory. They looked through their telescope that night and found it. And then, fast forward something like 10 years or so, there were similar deviations from the expected orbit, but this time with the planet Mercury. So Mercury wasn't behaving quite the way that Newton and Kepler would have predicted. And so if it worked once, it might work twice. And so Le Verrier predicted the existence of another planet interior to Mercury that was causing Mercury's orbit to be perturbed. And so for a long time, people were looking for it. And it wasn't until Einstein came along and said, oh, actually, Newton was wrong. Gravity actually behaves a slightly different way, and therefore there's no need for this additional planet.
Some of those things actually, before we get to that, let's talk about your somewhat circuitous route to being even involved in Kepler, because that's not where you were going at the beginning, and you talk about that in the first few pages.
Right. So I had applied to a bunch of graduate schools. I'm a physicist by trade and by heart. So I moonlight as an astronomer, but my approach to a lot of the kinds of things that I work on is really from the physics standpoint. They are slightly different disciplines. They overlap a lot, but so I was a physics graduate student, and I had planned on working in cosmology, which is the study of the properties of the universe and, the dark matter, dark energy kinds of things, black holes and the large scale structure of the universe and how galaxies cluster together, that kind of stuff. So that was my plan going into graduate school. And there was someone that I was planning to work with at the University of Washington. It was Craig Hogan. And the year, like right before I arrived, he was promoted from just regular faculty up to become the dean of the College of Sciences. And so he stopped taking graduate students. So I showed up. I had turned down a number of, so schools that I would have been really proud to brag to my friends about at my high school reunions, including my dream school. So my dream school was to go to Cornell because it's like Harvard, but it's not Harvard. Everybody and their dog wants to go to Harvard, and so that would have been something. Oh yeah, I've heard of that one. That's a pretty good school, isn't it? But it just didn't work out. My wife and I visited all the places, and we're like, no, we should go to Seattle. We should go to the University of Washington. So I went there, and my advisor, or the person I was anticipating working with, stopped taking students. And so I kind of bounced around for a couple of years from one research group to another, trying to, just kind of make my way through graduate school. And one of my early advisors said, hey, you should take a look at the new guy. He's coming in to replace Craig, and he works on the cosmology type stuff. So he brought me, we exchanged some emails, and then decided on a project which was going to be looking at what the black hole would look like at the center of the galaxy if it was observed with VLBI, like very long baseline interferometry. So the images that we saw a couple years ago about the black holes in the Milky Way and in it was M80 something or other, M81, I think. The images of the black hole that were taken with that Earth-sized network of telescopes, that was what I was supposed to do as a graduate student. So, but I hadn't had the right classes yet, and so he said, well, here's a practice problem. The practice problem is that if you have a planet that's transiting a host star and you put another planet in the system, then the gravitational interaction between the planets in that system will cause the time interval between successive transits to vary. So sometimes it'll happen early, sometimes the transit will happen late, and let's see what we can learn from those kinds of variations. So we had this practice problem. It was only supposed to take a few months. It ended up taking 3 years and producing a dissertation, and it ultimately was the thing. It was the piece of work that got me onto the Kepler mission. Because had I not done that, they wouldn't have needed any expertise that I had. That was what I brought to the table.
Funny that the one course you hadn't taken was general relativity.
So it was, but I mean, it worked out. I still really enjoy learning about cosmology, and I did eventually do some dark matter experiments on my own. Well, not on my own, but I led a dark matter experiment at Fermilab when I was a postdoc there. So, and I still had the opportunity to work with Craig Hogan because he followed me to Fermilab. He didn't follow me because I was there, but he followed me because there was a job opportunity and he went back there. But we worked together on a couple projects. So eventually the person that I originally had planned on working with was someone that I did work with when I was in Chicago.
One of the things that struck me, because it would be so frustrating to me, is the fact that once you got involved in the project, I mean, getting involved in the project doesn't mean really much of anything in NASA. You're vetted and vetted and vetted. It's got to be frustrating because you never know whether you're going to move to the next level of a possibility of budgetary constraints or some other thing seeming more, for want of a better word, sexy.
Yeah, I mean, NASA always has a perennial challenge of the funds aren't really that great. I think it's a little disheartening when people say, NASA wastes a whole bunch of money. And I'm like, NASA doesn't have enough money to waste when you compare it to anything else in the federal budget. So it's 0.5% of the federal budget goes to all of NASA science. All of NASA in general, not to mention NASA science, which is just a fraction of that. And so getting money from NASA is, it's not as common as it might sound. It's not like they're really rolling in cash, especially when they have big projects. As science continues to develop, it takes more sophisticated instrumentation to keep pushing the boundaries. And so instead of building a $100 million spacecraft, now it takes $250 million, and then it takes $1 billion to make something. And that's just the nature of when you're trying to look for something that's smaller, fainter, harder to find, different wavelengths. The technology doesn't magically get cheaper simply because you need it. And so that squeezes a lot of the research that happens at all different levels.
Yeah, and it took, what, 3 or 4 different iterations before you finally got approved.
Yeah, so for the Kepler mission, now I was in high school when it started, when it was first proposed. And so Bill Barucki, or I call him William in the book, but we always knew him as Bill in the science team meetings. So he was, he'd been working on Kepler since 1984 when he published his first paper, like devising, like what would it look like to build a mission like this. And he first proposed it for real funding in 1992. And it was rejected in 1992, and 1994, 1996, 1998. And every time it was going back, you need to prove that you can do this, you need to show that you can do that. And if only it looks really promising, but it's too risky. Okay. And eventually in 2000, when they submitted the proposal in 2000, that was the one that was selected. And so they were able to start building it in 2001, and I joined in 2008, right before launch. So they did all the work, and then I got to swoop in at the last minute and take a bunch of the glory with me.
That was another thing that I would be so scared. You begin the book by having you guys standing, watching the launch. And after all of this, I would just be so petrified. Were you guys really scared that?
Honestly, the NASA people weren't. I mean, I was a little nervous. The NASA people weren't really. I mean, things just got ticked off. The checklist. Okay, now we're at this altitude, and these things came off, and everything's going on time. The one thing that had happened was that just 2 weeks before, there was this orbiting carbon observatory, OCO, I think is the name of the mission, and it crashed. It launched and then immediately hit the ground because the fairing, which is the capsule that protects the spacecraft when it's in low altitude, it was supposed to burst open, and when it didn't, then the rocket was too heavy and it just crashed into the Earth. So that had happened just a couple weeks before, and so there was big concern. One, is that going to happen with Kepler? And two, is that going to is it going to push the launch date back? Do we have to run a bunch of tests, which is going to push the launch date back, which would be like 6 months later? The launch date only slips in one direction, so it would have been pretty hard. Like, okay, we're a week away from launch. Okay, now we're 6 months and a week away from launch.
Yeah, I like the way NASA now says it'll launch no earlier than. They never said it before, but now it always says no earlier than. They will return no earlier than. I don't know if it started with the Starliner, but it definitely is every single launch now. What was I going to ask you? Oh, so everything in the book is like nothing that I would do. I mean, you pick up a book, you go to a chapter, you go to a page, or you do calculations for a suspension bridge. And while they're incredibly complex, or building or coding or building a 737, which is a million parts, everything you did is so tight. I mean, it's so minuscule that it's almost hard to comprehend how it could even be accomplished.
Yeah.
You guys, I don't know, were you thinking that at the time? Because it's so, I can't put it into words really.
Well, the data, I mean, the data are really simple for an individual star. It's a string of numbers that give you the brightness of the star as a function of time. And then somehow included in those data are the variations in the sensitivity of the camera, the focal size of like the focal length. As the camera heats up in one direction or another, it's going to stretch in some ways. So that's going to change slightly what the focus is. You've got the stars themselves that have their own astrophysics going on. You have planets going around them. The stars have spots. The instrument has electronic noise that's causing variations, and then it goes into safe mode, and the whole thing gets a hole in it. And so, but you just have a series of numbers, and you have to tease out an Earth-like planet orbiting a distant star, and it's really the equivalent of looking at Las Vegas from space and identifying individual bugs as they're flying around the streetlights. And that's the size of the signal. It's actually looking at 3 copies of Las Vegas, because Las Vegas only has 50,000 streetlights apparently. And so it's looking at 150,000 stars and just identifying individual planets as they transit. And they're rare too. So if you look at an Earth-sized planet in an Earth-sized orbit, you have to get 10 parts per million in terms of your sensitivity, and you have to have, the transit only lasts for like 12 hours. So you have 12 hours out of every year that you can see a 10 part per million change in brightness. And that's your job, is to find that.
The other thing I thought about was, you're talking about 95 megapixels. And what if you had the luxury, like a Christmas morning, of, how, they say the computers taking the Apollo program are as powerful as my iPhone in 1969. So if you were building it today from scratch and it was like a Christmas morning, what would you be able to do in terms of clarity and, I guess magnification, specifications that you couldn't have done when it was designed back then?
So I think because there had been a proposal circulating around after the Kepler mission ended about rebuilding basically a copy of the Kepler mission, because one of the things that Kepler provided that no other survey since, and like before or since, has provided is the long time baseline. So looking at a single patch of the sky for 4 straight years, because typically these kinds of surveys you'll look for. Even now the mission that's currently flying called TESS, most of its targets it only observes for a month, and then that's it. And so Kepler, with this 4-year time baseline, there's nothing right now that competes with that. Even proposed missions don't have a 4-year observation plan. So the proposal was to basically rebuild Kepler, and the only thing that would have really changed is, one, they probably would have had more reaction wheels on it, so that because that was ultimately the thing that caused it to fail. And the other thing is just cleaning up the electronics so that there wasn't as much crosstalk between some of the wires, because that introduced some noise that was an issue. But I suspect that some of the CCD technology might be a little bit improved, but Kepler's CCDs were pretty good, and so they may change I don't think that they would necessarily change the format. I think it was pretty well optimized, and it's really just lowering the noise from the instrument itself would be the main priority.
Yeah, you mentioned the reaction wheels, and you also talk, not enviously, but you compare it to Spirit and Opportunity, which have a 90-day life and last for 16 years, or Voyager 1 rebooting its 1981 antenna to say, hey, I'm still alive. But then the reaction wheels failed sequentially. So what, to the layperson who is going to be listening to this or buying the book, what are reaction wheels? Why are they so crucial to a mission like Kepler?
Okay. So in order for Kepler to really get the measurements that it's looking for, so the specification was 20 parts per million, was the 20 parts per million in 6.5 hours. That was the goal, or 6 hours. And so meaning that you can see changes in brightness as small as 20 parts per million. In order to do that, the telescope has to be pointed extremely precisely, because if the telescope drifts at all, the pixels on any camera have different sensitivity across the pixel. So even though you have 95 megapixels, any individual pixel is going to be more sensitive in certain parts of the pixel than in others. And so if the telescope is drifting at all, or gets hit by a micrometeorite and isn't able to return to the exact original pointing, then you're going to introduce 10 part per million noise into the system, simply because the spot is drifting across the camera. And so the real precise pointing requires these reaction wheels. So reaction wheels are basically, if the telescope starts to drift, it'll start to rotate because of any variety of things, radiation pressure from the sun, or specks of paint that chip off and go in different directions. The reaction wheels will spin in order to basically absorb that angular momentum and return this spacecraft back to where it was supposed to be pointed. So the fine pointing capabilities of Kepler was driven by these reaction wheels. And there were 4 of them. It takes 3 to orient it in space. You need to be able to rotate 3 different ones in order to control all 3 possible rotation axes. So there were 3 that you need, 1 to control each direction. And then there was a spare. And one of the wheels started failing pretty early on. And so they booted up the spare and used the spare, and then the spare started to fail. And then eventually they went from 3 reaction wheels to 2 and then to 1. Or, 4 reaction wheels to 3 and then to 2. And at that point, then you can't point anymore. You can still point, but it's not the high precision pointing that you need. And so the original Kepler mission basically died when that reaction wheel failed, the second reaction wheel failed.
Right.
And they're only the size of they're the size of like a baseball, so they're not very big. And that's the whole enclosure. The wheel is actually smaller, the whole thing.
That's amazing. Well, so if we begin, like, I guess, deductively, one of the first things you talk about after the mission was in progress and in full mode is the idea of these, well, you talk about the scientists who said there's 3 in 2 chance that a star is binary. Mm-hmm. And then, so you got to deal with binary stars. You have to deal with brown dwarfs. What are almost?
Yeah, stars? So you have to deal with brown dwarfs. You have to deal with giant stars that are distant giant stars that are contaminating the field because the giant stars are brighter, and so you get more distant bright stars that will fall into your survey. And a giant star is, it's like 100 times bigger, 100 to 1,000 times bigger than the sun. And so there's no way to see a planet orbiting something like that.
Right.
Any that would even survive to that point.
Looking for stars in daytime. Or when you sometimes see the moon in daytime. Well, what about the fact that early on, the conundrum and the big question was, why are these Jupiter-sized possible planets orbiting so closely to this star?
Yeah, so that was kind of one of the big questions. It still is an ongoing question, although I think we've resolved many of the initial issues, but we still have some unanswered questions related to it. But the first planet that was ever discovered orbiting a star that's like the sun was a Jupiter-sized planet on a 3-day orbit. So everyone that worked in exoplanets got the same lesson that I did, that you have this disk of gas that the planets are going to form from. The inner part of the solar system is too hot, and so it's too hot for water to condense, for water, methane, ammonia, carbon monoxide, those kinds of things. And so those compounds, they stay in the gaseous form in the inner solar system, but in the outer solar system, they'll condense. So the first location where the material is able to condense, you're going to have an overabundance of material that you can form a planet from. And so you get giant planets right at that edge where, like, what's called the ice line, where now all of a sudden there's a whole bunch of water that condenses, which gives you a whole bunch of mass that you can use to build your planets from. So Jupiter and Saturn form outside of the ice line because that's where all the volatile materials are. And so that was the assumption for, 250 years, that Jupiters all form out at 5 AU, and so that's where you'd expect to find them. So to have the first planet discovery be a Jupiter mass planet on a 3-day orbit, which is 10 times closer to its star than Mercury is to the sun, like, nobody was ready for that in terms of, like, our theories weren't ready to predict something like that. How do you get a planet like Jupiter that close to the host star? And so there were a number of theories that were proposed, mostly around the time that I was in graduate school, because it was only a few years. That was discovered in 1995. I started graduate school in 2001, so it was pretty young. And over time, some of these models have been rejected. So in terms of, they've been rejected in that they are not the primary mechanism to form hot Jupiters. So one of them would be, if you have a really massive disk, then you'll have a whole bunch of planets that form all of a sudden. Like, you'll just get a chain of pearls that form out of some kind of wake in the disk, and then most of them get ejected, and some of them smash into the star, and whatever's left over, that makes a hot Jupiter. Other proposals were that, you have a Jupiter embedded in a disk, and then the friction between the giant planet and the disk is going to cause it to drift inwards, or it's going to create a wake, and then it's going to interact with its own wake gravitationally, and that's going to drag it inwards. And then what I think is probably the prevailing mechanism to produce hot Jupiters is that there's some kind of dynamical effect on a Jupiter mass planet out. So Jupiter forms where our Jupiter formed at 5 AU, like 5 times the distance from the Earth to the Sun. And then either a star or another planet that's nearby causes its orbit to become highly eccentric. And when it becomes highly eccentric, then its orbit takes it really close to the host star. So like if Jupiter were to become highly eccentric, it would come close to the sun. When it gets close to the sun, the sun would try to stretch it out. Just like when you fall into a black hole, you get stretched out. The same thing happens when you get close to the sun. It would start to stretch out. That would, the friction inside of there would cause it to heat up. The energy to heat it up has to come from somewhere, and it generally comes from the orbit, and the orbit would start to shrink because of those interactions. It takes a while, but that's probably the dominant mechanism that we believe is responsible for producing these hot Jupiters. But, that's a 25-year, actually almost 30 years now, set of measurements that have been made that kind of point in that direction.
Stable orbits?
Yeah, so the orbits are stable. So they're stable to a point. There are a handful of Jupiter-sized, these hot Jupiters, where they can cross a threshold. And the threshold is that if the planets orbit the star faster than the star rotates, then so you have a planet, it orbits the star is going to change its shape slightly because of the tides. The planet's going to raise a tide on the star. If the star rotates slower than the planet orbits, then that tide is going to lag behind the planet. On the Earth, because the Earth rotates faster than the moon orbits, the tides on the Earth lead the moon. But if you were to switch those roles and the moon were to orbit faster than the Earth rotates, then the tides would lag behind the moon. So that's what happens in these planetary systems. The star spins slower than the planet orbits, and so the tides lag behind the planet, and then that causes the planet to drag inwards, and eventually will cause it to be engulfed. It's called Darwin instability. It's named after, I think, the son of Charles Darwin was an astronomer. And so that instability is something that can come into play, but it takes a long time for that to work its magic. And only with the shortest orbital, I think there's one planet that we've seen where we can see the orbit decaying after we've observed it for 20 years. We can see a 2-second change in its orbital period or something like that.
That's amazing. For the readers of this book who are searching for something, especially the subtitle of the book with regard to how all this gives us pause with regard to our own situation, kind of in this strong anthropic principle, and you delve into that slightly. When did you move from those Jupiter-sized planets to a situation where you found, this is in the Goldilocks zone. This could be something that's very much like our Earth. This is something where life could actually originate. When did that happen? If it did.
There wasn't a single moment when it happened. It was kind of a series of discoveries, kind of milestones. Like, for example, Kepler 10 was the smallest planet that Kepler had discovered up to that point. It was only in the first few quarters of data, but it was a planet that was 1.25 times the size of the Earth. And so it was a milestone that we found something that is almost Earth-size, not quite Earth-size, but almost Earth-size. And then now we found one that's in the habitable zone of an M-dwarf star. And now we found one that's in the habitable zone of an F-type star. And now we found one that's smaller than the size of the Earth. And so those were a series of discoveries that all kind of benchmarked the progress of kind of peeling back the veil behind an Earth-sized planet in an Earth-like orbit. And of course, NASA is really good at milking discoveries. It would be nice if particle physics was similarly capable of milking discoveries to the same degree. But each one of those benchmarks. Now we found a planet. So maybe we'll find a large planet in the habitable zone that could have a habitable moon. And then you find a small planet, and then the small planet close to the habitable zone, and a small planet in the habitable zone. And it was really just kind of one benchmark at a time. It seems as though now something on the order of 25% of stars have a planet in the habitable zone. And most of those are going to be Earth-like, or like 25% are Earth-like planets in the habitable zone. But that's an estimate that's really relying on data that was at the edge of what Kepler was able to detect. One of the issues that we faced, and I don't know if I actually brought this up in the book. One of the issues we faced is that we assumed that the typical star like the sun would have noise properties like the sun, that it would have flares and things like that were comparable to what the sun has. It turns out that most stars like the sun are actually slightly more noisy than the sun. So the sun is on the quiet side of different stars of its different peers. And a consequence of that is that Kepler wasn't quite as sensitive to Earth-sized planets as we expected, because the noise from the stars was bigger than we expected. So it was able to see something on the order of a dozen planets in the habitable zone that were similar to the size of the Earth. And when I say habitable zone, like 300 to 400-day orbit that were roughly the size of the Earth. And from that, we draw these conclusions about how many Earth-like planets we would expect in the habitable zone.
You mentioned M stars, and I think people won't understand how different type stars can affect not only the planets, exoplanets you find, but the characteristics that they might have.
Right. So the astronomers, we have a bad habit of adopting language from the first people that talk about it, and then we have to carry that baggage with us forever. And the stellar classifications is an example of that. So back in the day, stars were classified based upon how prominent the hydrogen lines are, and it went all the way from A, B, C, D, E, F, G, down to P. And then it was realized that we were doing it wrong. The physicists came along and said that the astronomers were doing it wrong and that they needed to do it a different way. And so they were rearranged in order of temperature and basically in order of mass to O, B, A, F, G, K, M. So the sun is a G-type star, which is kind of right in the middle of that classification system. And M stars are smaller than the sun, typically around half of a solar mass, but they go down to about 1/10 of a solar mass. And they're physically different than the sun. So the sun has 3 layers in its interior. It's got the core, it's got a radiation zone, then it has a convection zone near the surface. M-type stars have no radiation zone. They have a core and they have a convection zone, and that's it. They are significantly less massive than the sun. They're a lot dimmer than the sun. They could be 1,000 to 10,000 times dimmer than the sun. What that means is that the stars, or the planets that orbit around them that get the same amount of light that the Earth gets, and therefore could have liquid water on the surface, are much, much closer to those stars than the Earth is to the sun, which means they have a higher probability of transiting. And so that was one of the reasons that Kepler was looking at M-dwarf stars, is because the probability of a transit is much higher, and because the stars are smaller, any transit is going to be more prominent to be able to see them. So that was a place that people have been looking for a long time, as this is the golden opportunity to find a habitable zone planet. There are some issues with that, though, because, for example, the sun and the planets around the sun form in a few million years. Well, like Jupiter forms within 5 to 10 million years. The Earth forms in several hundred million years, so it's a different process. So Jupiter forms very quickly, and the sun forms really quickly. The sun forms within a few million years. M-dwarf stars, they take tens of millions or hundreds of millions of years to form. And so there's a question about, given how long it takes for these stars to form, do they boil off all of the water out of the system before the planets form? And we don't know the answer to this. If M-dwarf stars are going to be completely dried out because of how long they bake before the planets are made. So while the traditional habitable zone is easier to measure, it's easier to find planets that are in there, it's not obvious that the planets are going to have quite the same composition that the Earth has, given the fact that the formation timescale is a lot longer.
Well, given what you're talking about in the PR department of NASA, getting information out that makes people excited, although particle physics, I mean, the God particle really got everybody going.
It
Um,
it did,
um,
but those are a bit more rare. Um,
uh, yeah, true. If you got a standard model and you're really, well, gravitons. Anyway, what I was going to ask you was, in your heart of hearts, this is the question that people really, and it's exactly what you're talking about. If you say that 25% of stars and you multiply it out by how many galaxies there are and how many stars in each galaxy and how many planets therefore, and then how many terrestrial planets there are, what in your heart of hearts do you actually believe that there is, starting with SETI, that there is abundant life in the universe? Do you really believe?
so I personally don't. I can easily imagine that there's a lot of life out there. It's not really the question that motivates me, but I know I know how to toe the party line on this one, and I am glad that there are a lot of people that is the main thing that drives them. My personal research is more about how do the histories of these planetary systems compare to the history of our solar system. But a friend of mine, David Kipping, he's on this search for his main thing, at least as it relates to Kepler related stuff, is finding moons, trying to find a moon that goes around another planet. So looking for an exomoon. But he just had a video. His YouTube channel is the Cool Worlds YouTube channel, and he just had a video where he talked about. I guess he was comparing how likely it is to form life on a planet based upon the earliest time that life appears on the Earth. So basically saying, if life doesn't appear on the Earth for 2 billion years after it forms, then that means that it's hard to get life going, and therefore life would ultimately be rare on other planets. But the earlier we find life on the Earth, the easier it is for life to form, and therefore the more likely life would be on other planets. And I guess there was a recent discovery from the biologists where they found some evidence for life on the Earth that's like, as soon as water could rain onto the surface and stick, basically. It was really, really early. And he said, when I plug this into my formula, he has a formula that says, if life happens at this time and here's the age of things, then this is how likely it is for life to form somewhere else. He put it into his formula and the number was just like through the roof. So through the roof with the caveat that, these are estimates for different things. But it went from a relatively low probability to a relatively high probability. And he was basically saying, with this discovery, it actually means that life probably is much more common than we expected, 10 years ago before some of these things were found. Like small micro fossils in some rock that has, some age on the Earth.
Yeah, it's funny how you guys all have your passion and what you said about in your heart. Because this one guy I just interviewed wrote a history of the egg, which was actually fascinating because eggs aren't life, but for them. And she talks about cyanobacteria, being around since the very, very beginning, and similar to what your friend believes. But if you go back, well, let's go back to the hardware, because behind you, you have the image that I know what it is because I read the book, but that's, I guess.
So this right here,
yeah.
that's the Kepler first light image. So I run an art exhibit every few years at UNLV. That's a scientific art exhibit. So I have a whole bunch of. That's not the only one that I've got. I've got several of these pictures that people don't pick up. That was done by one of my undergraduate students at the time, and I had a copy made for myself. So this was made for that art exhibit, but this is the first light image from Kepler. It shows the field of view. So there's 42 CCD chips. Each one of them is kind of paired up. You'll notice that with the exception of the one in the middle, so that's this one, with the exception of the one in the middle, there's a fourfold symmetry. So it rotates around. If you rotate it 90 degrees, it looks the same. And that was because, so that's the Kepler footprint. This on the sky is about the size of the palm of your hand at arm's length. So if you hold your arm out, then the Kepler field of view would fit inside the palm of your hand. That's very different from the field of view of like the Hubble Space Telescope. So the wide field camera on the Hubble Space Telescope, if you were to hold a penny at arm's length, the wide field camera would fit inside the eye of Abraham Lincoln. And so this is a huge field of view by astronomy standards. And it was designed, the footprint is designed like this so that, one, they can put really bright stars fit in the gaps. So they put the brightest stars in the gaps because those would saturate everything. They would like blow out all of the other targets that they were looking at. And then they need to be able to rotate this field as Kepler orbits, because Kepler orbits the sun, it doesn't orbit the Earth. So it's orbiting the sun, and it needs to, every quarter of its orbit, change where the solar panels are pointed in order to keep it, well, to keep the telescope powered. And so it would rotate this field of view. And so you'd have a star that would be in this pixel, or like in this camera, in one quarter, and then it would be moved over to this one, and then it would be moved down to this one every roughly 90 days. It's a 372-day orbit for Kepler. It's slightly longer than the Earth's orbit. And so that was the first light image. Some of these chips, some of these modules, so a module is a pair of chips. There were 3 of them that ultimately failed. One of them failed fairly early on, like within the first year or so. And then there were 2 others that failed over time. I mean, ultimately the telescope itself lasted for almost a decade, even though the mission itself, the mission ended when the fine pointing capabilities were gone, but they were able to repurpose the telescope with lower precision, but still keep using the camera, because the camera was still functioning pretty well, for another basically 5 years. So it was like 4 years in one, 5 years in the other operating mode, and then at that point it ran out of fuel, so there was nothing that they could do with it after that.
Hydrazine. That's just, when you talk about the eye of Abraham Lincoln, or looking at Vegas, or in the old days when they said you could see a basketball at 10,000 miles, obviously it's much better than that now. But the idea of having those big stars in the gaps, to me, it seems like a million Rubik cubes that you had to design. Mm-hmm. It's unfathomable to me in my mind.
Yeah, so when I joined the mission, because I joined in 2008, about a year before it launched, and they were still choosing which stars to look at. So they have millions of stars to choose from, and they had to narrow it down to about 150,000.
But you had to
Yeah, and then you have to orient it in the right spot and get it. Well, and the other thing is, so it's hard to see here, but these pixels down here, they're brighter. They appear brighter than the ones up here. That's because the plane of the galaxy would be basically kind of right where the book is. And so you have more dense star field here, and then a less dense star field as you go towards the top of the camera. And the issue there is these are 95 megapixels, but these pixels are gigantic. They're compared to, I think they're 500 times. The numbers in the book, it's not something I remember off the top of my head, but they are many, many times larger than the pixels on Hubble. So Hubble pixels are tiny, which means it can make really fine, detailed images. These pixels are big because they need the large format for the camera. And this is not really designed to take pictures of these systems. It's designed just to measure how bright they are. So how highly resolved the images are is less important than how accurately it can count the brightness or measure the brightness. So if they were to have many stars in the field of view, then a lot more stars would overlap each other, and it would look like a single star. There's a confusion limit where you can't tell if that blob of light is from 1 star or 2 or 3 or 10. And so you have to be away from the galactic plane so that you get single stars. But if you're too far away from the galactic plane, then you don't get enough targets to be able to see. You need to have 100,000 something on that order in order to make the measurement you want to make. And so you can't get too far away from it, or else you don't have 100,000 target stars. And so there's basically an optimum value where you get enough target stars, but it's not confusion limited. And that tells you how far above the galactic plane you need to point the telescope. And then you have to say, okay, given this footprint, how do we orient it so that we don't have really bright stars that are going to blow out the image from everything else?
I like the term confusion limit because it's not really a scientific term, but if you use it as a metaphor, it's no real different than the human race. Mm-hmm. We all have this confusion limit where you have a certain amount of tiny objectivity, and then things, especially for each of us individually, begin to differ from somebody else's viewpoint. And for each of us, that could be the beginning of our confusion limit. But that's beside the point. One question I did want to ask was, in that image, why is it not a perfect rectangle in terms of the panels, the pixels? There's a reason why, and I forgot what it was.
Well, so they have to have the wiring. So the wiring that gets fed from the chips down to the instrument, like where the data gets stored and then ultimately downlinked to the Earth. So there has to be gaps in it so that they can situate where the wires run. It has to be, one thing that is missing from here is in each of these corners, there was another small detector in each of those corners, and that's used for the pointing. So basically, there's a star map, and how does Kepler know where it's pointing? It knows where it's pointing because it has certain stars that are lined up inside those four. They're fine guidance sensors is what they're called. And they would read these like many times per second. They would read them out to make sure that the stars that were supposed to be in those areas were still in those areas and in the right spot, because that's how you measure where the rest of the camera is pointing. So it basically has these four sensors that are used to constantly monitor the orientation, the attitude of the spacecraft. And then it uses the reaction wheels to keep it pointing in the right direction.
It reminds me of a QR code, how they have the three blocks in the three corners to stabilize it so you can start from there. Because if you don't do that, then like you said, once the reaction wheel goes, it's just kind of fuzzy. Not fuzzy, but streaked.
Yeah, it drifts, and even if it doesn't take much drift. So for example, the amount of drift that it takes to go out of fine point, which means you go from science quality data to not science quality data anymore, is the equivalent of if you were observing the Washington Monument from Los Angeles and you're pointing, initially your telescope is pointing at the tip of the Washington Monument viewed from Los Angeles, and it drifts down to the bottom of the Washington Monument as viewed from Los Angeles, then you're out of fine point and it's not science quality data anymore.
Those analogies, metaphors are amazing to me because it goes back to my first question is how the hell did you do this? But talk about the actual roll up your sleeves and get this done thing. So here you have a star, there's a transit, and you measure the transit, and you only have a certain amount of time in which to do it, but you can do it for a year or more. Then somebody on the planet is analyzing this constantly to see whether this is it. I mean, the data comes down. Actually, you talk a little bit about how the data comes down, right?
Yeah, so it comes down through the Deep Space Network.
Computer. Yeah, the giant computer.
Yeah, so the data come down through the Deep Space Network, which is the world's most expensive internet service provider. It's the way that you communicate with anything so low Earth orbit, you can communicate basically directly with ground stations. But with things in deep space, so these are the planetary science missions to Jupiter and stuff like that. They send the radio signal to these big radio antenna on the ground, and that's because it's radio frequency. It doesn't have the same bandwidth that like 5G networks would have, because that's in the microwave, which is much, much, much shorter wavelengths, and so you can get more information into shorter wavelengths. So they downlink the data, and then they feed it into this computer at NASA Ames called the Pleiades cluster. And I've been in the room once, and it basically is like a grocery store, a small grocery store, but still a grocery store sized thing. I mean, maybe like a bookstore sized room that's just lined with rack after rack after rack of computer CPUs. So the data would come down, it would get processed. But then it would get processed, cleaned up, we take out the temperature fluctuations, we look at the brightness of the stars, we compare them to each other, we get a time series for each of the things, and then you have to look for planets that have different orbital periods. The way it would look for planets with an orbital period, it would look for a dip in the brightness, but it would do it by taking the time series and then chopping it up into, say, if it's looking for something that's a 3-day orbit, it would chop it up into 3-day periods, stack them all on top of each other, and then look for, because all those images are added together, it would find the dip in the transit. So then it looked for 3-day periods, and then it looked for 3.05 day periods and 3.1 day periods and 3.15 day periods, and it would just keep slicing the data, keep stacking it up, and then keep looking for the dips. So it would do that, and then that would produce the catalog of potential candidates. The issue was that as the mission went on, every time you bring new data down, you have to do that again. So you have to take all the data and start over, cleaning everything up, chopping it up into 3-day and 3.05 and 3.1. And so as time went on and you get more and more data, it takes longer and longer and longer to analyze the data because you have to start over each time. Because if you're looking for something that's a 1-year-long orbit, you're not just going to rely on the first measurement. You have to take the whole time series and then add everything together. So they reprocessed the data. It was eventually got to the point where it was taking more time to analyze the data than the time interval between getting data on the ground. And so they had to keep optimizing the system. And so the data analysis from the Kepler mission went well beyond the lifetime of the flight segment, the flight segment being the spacecraft and its observations. So that ended in like 2012, 2013. I guess it was 2013 when it ended. And the analysis continued until the final catalog was like 2018. So it had another 5 years of development and analysis and then redevelopment and getting the humans as much as possible out of the analysis business and having it done by computer. Because humans are fallible, like we have different, once your eyes get blurry looking at the 20,000th transit, it might not look quite the same as the first one that you saw. And so there was a lot of development and analysis that went after the mission itself had ended to produce the final catalog that came out in 2018. Now, the group that I work with, we still meet regularly to analyze the data. We published our own catalog with improved measurements of some of these things just earlier this year. So there's still work being done on the Kepler data.
Yeah, so my last two questions would be, one, with AI, with faster processing speeds, the original data is always going to be there. Can finer and finer analysis or correction by AI yield even more than you had? All right, yeah, you went through it to 2018, but it's 2024 and soon 25. In that interim, or in the future, will there be more sophisticated instrumentation that could even drill down finer with granularity?
So it's not so much the instrumentation that is the final improvement, but it's more, okay, so here's a bit of insider baseball. I don't know if I'm supposed to share this, but I'm going to anyways.
Yeah, please.
Because I served on a review panel. I've served on a number of NASA review panels, because it's kind of part of the job when you're a professor to review other people's proposals for NASA. And one of the things that came up was the group at NASA Ames, because that's where the data analysis was done. They had proposed to do basically take all the knowledge that they had, having worked with the spacecraft for 20 years, or I guess like 15 years. So these are the people who understand the personality of the spacecraft the best. They know like what the noise looks like. They know all of these details about it. And they were saying, now that we have all this information, if we were to start over with our analysis, we would do it differently. We would do these things. And that would improve our estimates for our measurement of A to Earth, which A to Earth is the frequency of Earth-sized planets in the habitable zone of sun-like stars. So these are the people in the world who by far have the most expertise as it relates to the Kepler data. And so for a while, there were other people who started proposing to do like, we're going to do a final analysis of this stuff. And after one of the review panels, I was like, look, this is valuable stuff, but the people who should be doing this study are the people at Ames who know who've already worked with the data. And I said, I don't know how is this information supposed to be communicated up to headquarters that this is a valuable thing? The reason it's important is a fewfold. One is that the people at Ames aren't getting any younger. And so eventually that expertise is going to age out of the system. They're going to retire and then the expertise is gone with them. And so if NASA wants to get this measurement as best as they possibly can, then they need to basically liberate the people at NASA Ames to give them the opportunity to work on it. Because, you're supposed to work on projects that NASA approves, and so they need to get some kind of internal approval to do this analysis. And so that was given, I don't know if what I told them, if they were already planning on doing it, or if what I told them was influential, but I was gratified to find that they were given kind of a one last shot to analyze the data from Kepler. It's ongoing now, because so they were approved. They had some money to hire some postdocs, but it takes 18 months or so to bring a postdoc on board. And I think they're in the middle of it. We probably will hear something in the next couple of years about the results of their study, which will be the best measurement of the number of Earth-like planets in the habitable zone of Sun-like stars, probably that we will get for the rest of the century. Because I just don't see any other missions competing with Kepler that are on the horizon.
I always like when I hear about the guts of things, and also if I can get someone on an interview to tell me things they're not supposed to tell me.
So I suspect it's okay for me to say this, but it is kind of the internal workings of, and the...
A year and a half for a postdoc. Yeah, it's like...
Well, because they get the award, and so you can put out an ad that you're hiring a postdoc, but you have to wait till the end of the academic year for the people to graduate, and then they do the interviews, and then they come the next year, and...
Well, yeah, kind of answered the second part of my question, which is how I was going to end the interview, which is, okay, well, Kepler, for want of a better word, died, but the data's still there. That's one side of it. But there's got to be something, well, it doesn't have to be. You're saying the end of the century, but there's got to be something new that you or somebody like you thought of, that either from the ground, although it would be much harder, or from something like the James Webb Telescope, which is not going to happen given NASA's budget. But isn't there some type of workaround, or isn't there some type of idea? Like it used to be, Saturn V propels a projectile to the moon in 3 days. Now there's no money, so you slingshot it all over the place, and the Chinese take 3 weeks to get to the moon. Isn't there some kind of something that would allow you to truncate that time period when you say, which makes me sad that it's going to take till the end of the century to get any further along?
Well, it kind of depends on what further along means. So I think because what Kepler did, before Kepler launched, and as it was being designed, the solar system was the model for how planetary systems are built.
Exactly.
And so the assumptions that went into building the Kepler telescope were, how do we find a planet the size of the Earth in a one-year orbit? And that kind of drove everything. All the rest of the design was pushed, had that one goal in mind. Once Kepler flew and we realized that planetary systems, there's lots of planets, many more planets than people originally anticipated on shorter orbits, then you would actually change the design. So if we knew after Kepler what we would find, like had we known what we were going to find, we wouldn't have built Kepler to start with. We would have probably built TESS to start with, which is the mission that's flying now. And so Kepler found all these planets that are nothing like what we have in the solar system. They're bigger than the Earth, they're smaller than Neptune, which there's no examples of that in the solar system. They're on 10-day orbits instead of year-long orbits, so that the orbits are measured in weeks instead of months. And so the issue is that the Kepler targets are all far away because it was pointing in one part of the sky, and so in order to have the large sample, you have to look at more and more distant stars. So when you do an all-sky survey, which is what TESS does, then you can get the number of targets that you're looking for closer because you're looking in all directions, so you have all of the nearby stars that you're looking at. So the TESS mission is looking at the brighter stars, but those are discovery-type missions where they're all about identifying the targets, but they're not able to characterize the planets themselves. So you might be able to see a planet with a given orbital period, but you're not going to know what it's made out of. You're not going to know what's in its atmosphere. And so once the planets are discovered, you turn it over to different instruments to do the detailed characterization. And so a lot of exoplanets in the near future is going to be driven primarily by understanding what the planets are that we've already found, rather than just finding more of the same. So I think it'll be a while, maybe by the end of the century, or certainly like, I can imagine 50 years from now, something like that, that there will be another mission that's a discovery mission that would be basically a souped up version of Kepler instead of a remade version of, like, instead of making the same thing, you'd make something bigger that can observe longer orbital periods. By then, you might even have a different technology that you're using. So it might be that by then direct imaging is the primary mechanism that we use to find planets.
Well, I guess 50 years isn't too bad. And then again, if we're not here anymore, it doesn't make any difference anyway.
Yeah, so 50 years is outside of my horizon for, I hope that I'm still alive by then, but I'll be pushing the triple digits at that point.
Well, I'm not going to be here.
So there's nothing on the horizon that's like Kepler itself, but there are missions that are on the horizon that are doing subsequent science that Kepler wouldn't have been able to do in the first place. So studying the planetary atmosphere, studying the composition, measuring, is there carbon dioxide on these planets? Is there water on these planets? Is there ozone on these planets? That's really the next area where we're going to be looking for things. I guess another one that's coming up is, so the Roman telescope. Is it Roman? Yes, because there's a Roman telescope and a Rubin telescope. The Roman telescope is the NASA mission, and that's supposed to be launching, I think, by the end of the decade, which probably means at the beginning of next decade. But that's supposed to be launching, and that's a real successor to Hubble. So Webb is more a successor to the Spitzer Space Telescope. The the Roman telescope. So the Rubin telescope used to be called LSST, and that's a ground-based survey, all-sky survey. The Roman telescope is the one where one of the three-letter agencies was like, "Hey, NASA, we have these really expensive mirrors. Would you like two of them?" What these agencies were using with mirrors that you can get high-resolution images from looking at the Earth is, I'm not totally sure what they were doing with them, but NASA is planning on pointing them out in looking at, one of the things they're going to be looking at is doing planet hunting. And that telescope, the Rubin telescope, is going to be capable of even finding moons orbiting around planets like Jupiter. So it's looking at Jupiter, like right after Jupiter forms, it's still pretty hot, and so you can see the planets transiting in those circumstances. So there's a lot of instruments that are coming online that there's a lot more that we're going to be learning. That's not the discovery of a new planetary system with 5 planets with some orbital periods. That's a different batch of science that's not going to be quite as forthcoming as it's been with Kepler.
Well, I wish I could interview you 50 years from now, holographically, virtually, or mind melding, but maybe I can get my son to do it if you're still around. But in any event, thanks so much for doing this. It really, the book is great. I think the best part about it is that it's way accessible to people. I think the cover's good, which as a bookstore owner, cover makes a big difference. And it was a pleasure to read. I thought it was going to be daunting at first, but it was very accessible, and I really appreciate that when someone's writing about what people call popular science. So thanks so much for writing. Thanks so much for being here today.
Yeah, it was my pleasure. It was really fun to write. I'm actually in the middle of a second book, not about Kepler. It's a different book, but I really enjoyed writing this. I enjoyed remembering all of the events because I have 15,000 emails that I was like, oh, let me look and see if I can remember this email and where we had this exchange.
That was one of the reasons you turned the pages, because it's part biography, which is interesting.
So I appreciate it.
Sure. Nice talking to you.
Good to talk to you too.
Thank you for joining us for another episode of The Avid Reader. If you liked today's episode, check out more of our content on our channel.